Welcome back to another Regents Physics topic overview. Today we're going to be talking about friction in equilibrium. So let's get right into it. Alright, so starting off here with the definition of equilibrium, we have that this is an object that is moving in a straight line at a constant speed. This includes when it remains at rest, and forces in equilibrium are balanced, meaning that forces in opposite direction are going to be equal to each other. When we solve equilibrium problems, we're going to have a two-step solving process. We're going to start off with a free body diagram. That's essentially going to tell us which forces are going to be equal to each other. Then we're going to set up our equations of forces equal down forces and left forces equal right forces. For a free body diagram, this means that we have a labeled arrow that represents each force. Each force begins on the object and points in the direction in which the force acts. So if I'm pulling an object to the right or pushing it to the right, that force is going to go from the dot to the right. Then we're going to have a list of forces indicating the object applying the force and the object experiencing the force. I'll show this more when we make the free body diagrams. So let's move into some of our other facts. Starting off here, we have friction at the bottom. We're going to talk about mass and weight first. These are not the same exact thing. Mass is in units of kilograms. It's how much material is contained in an object. Weight is a force, so it's in newtons. This equation is going to end up being Fg equals mg. So when I have Fg on a free body diagram, know that's equal to my mass times my gravitational field strength of the planet. On Earth, that is going to be 10 newtons per kilogram. Also on the reference table, you have 9.81 meters per second squared. We just round off to 10 to make our lives easier. Normal force, that is a force that acts perpendicular to the surface. You'll see that in free body diagrams. A platform scale reads normal force if you see that in other questions. We have here for the frictional force. This is a force of the surface that acts along the surface, whereas the normal force is the force of the surface that acts perpendicular to the surface. Force of friction acts in the opposite direction of the object's motion. You have the coefficient of friction, that's on the front page of the reference table as well for different surfaces. This is not a force. This just tells us how sticky two objects are in relation to one another. This cannot change unless I change the bottom of the object being dragged across the surface or the actual surface itself. And my equation for frictional force Ff is mu, that coefficient of friction, times the normal force. So let's now get into our examples. All right, let's take a look at example number 1. The facts that I just had on the previous two slides are going to be in the description down below, along with the examples as Google Docs. My example here, the coefficient of kinetic friction between a 300 Newton crate and a level warehouse floor is 0.200. The crate is pushed at a constant speed to the right. This is one of the Regents questions where they give me the coefficient of friction. I don't have to look at the actual reference table to find it. What we're going to start off with here is my free body diagram. So having the free body diagram, my first force I should really always start off with on Earth is going to be the force of Earth on the object, or Fg. And last time I checked, if I drop something, it's going to fall straight downwards, so that force is going to be straight down. Then I'm going to say what the object is that is creating this force. Again, when we have a force, it's object on object. So it's not the force of gravity on the object, because gravity is not an object. What creates gravity is the planet that I'm on. That is planet Earth. So Fg is going to be the force of Earth on the crate. Then we are going to have all other forces must be contact forces. So what am I in contact with? I'm in contact with my hand pushing, and I'm in contact with the ground as well. So the first I'm going to go with here is my normal force. Again, that is the force that is perpendicular to the surface, and that is going to be the force of the floor on the crate here. Again, it's the object on object. Then I am pushing the crate to the right here, so that is going to be an applied force Fa. So I'm going to put that arrow there to the right. And the object that creates that is my hand. So we're going to have the force of my hand on the crate. Then my final force is going to be friction, since I've been given a coefficient of kinetic friction and it doesn't say a frictionless surface. I have friction here. Friction is going to be in the opposite direction of motion. So that's going to be to the left. And then I'm going to have the object on object that's created by the floor. So the force of the floor on the crate as well. This is along the object, not perpendicular to it. So let's move into part B of my example. All right, so moving into part B of my example, is the crate in a state of equilibrium? And we're going to justify our answer. So again, when we justify answers, we're going to start off with a fact of physics. That is my evidence. We're then going to explain that fact or a situation, how it applies, my reason, and then my claim is essentially just my answer. So we get a full idea of what's actually happening. So the first thing we're going to start off with here again is my fact of physics, what equilibrium exactly is. So we know equilibrium is when an object is moving in a straight line at a constant speed. This includes an object at rest. So that's going to be my evidence or my fact of physics. So what's actually happening here then is my reasoning based on this fact. I've been told that the crate is being pushed at a constant speed and it's along a level warehouse floor, so that means it's not like zigzagging or anything. So we know that this is being pushed in a straight line at a constant speed. So since the crate is being pushed in a straight line at a constant speed, we can then make my claim that this crate is in a state of equilibrium. It is also not moving up or down, so the vertical direction is also in a state of equilibrium as well. So that means we can use our equations: up forces equal down forces and left forces equal right forces. So let's move into part C of my example. All right, so moving into part C of my example, we're going to calculate the magnitude of the horizontal force required to move the crate across the floor at constant speed. We're going to show our work, including the equation and substitution units. Again, it means we're going to start off with one of our equations from the reference table and then plug in with the proper units. You can see here that I have my free body diagram. That was part 1 of my problem solving process. Now I want to set up my equations here. Since I'm trying to find the force that I'm pushing with to have it at constant speed, that's FA. I'm going to start off with left forces equal right forces, because that means that my applied force is going to be equal to my force of friction based on the fact that we are in equilibrium. So we have here left forces equal right forces. Then my free body diagram is going to tell me which of those forces they are. That is FA, the applied force to the right, and FF, the frictional force to the left. So FF equals FA. Now I can use my equation for frictional force here and plug that in for FF. On the Regents reference table, that's going to be on the back portion of that in mechanics. That is going to be my coefficient of friction mu times my normal force Fn. And that is going to be equal to my applied force. We don't know what Fn is at the moment, but we do know that the crate is not moving up or down, so it's also in a state of equilibrium. So we can do up forces equal down forces. So we're going to start off with that here. My up force is the normal force. My downward force is my weight, or Fg. So I can have here that Fn equals Fg. And I can go plug that into my equation here for Fn now. So I'm going to have my coefficient of friction mu times my weight of the object, because that's equal to my normal force, is equal to the force that I'm pushing with to the right here. Now, we can plug in our numbers. We've been given the coefficient of friction in the question. We don't have to go to the reference table to find that. So I'm going to plug in the 0.2. What's Fg? Fg is the weight of the crate. That is actually given to me in the question because it tells me I have a 300 Newton crate. That's like if I was told I had a 3 kilogram crate and I had to convert it into newtons. I've already been given the weight in newtons, so I don't have to worry about that conversion. I can just plug that into the equation. So I have my coefficient of friction 0.20. Again, that's a unitless number. And then you have there 300 newtons for the crate. That is my weight, or Fg. So I can plug those two numbers in there. 0.20 times 300 newtons. I'm going to plug that into my calculator and end up with my answer here of 60 newtons, which is equal to my applied force, or horizontal force that is required to move the crate across the floor at constant speed. So let's move into another example similar to this. We're going to have to use the reference table a little more. Alright, so example number 2 is going to be a fairly similar situation. So if you want to go ahead and try this yourself with the example in the description down below, you can. The only difference here is that I've been given the mass of the block instead of its weight. So I'm going to do that conversion when I get to that point. So a 5 kilogram block, a rubber block is pulled by a rope horizontally at constant velocity across a sheet of ice to the left. Also, the difference is here, we don't have our coefficient of friction given to us, but we're going to have to go to the reference table and we'll show that later in the example. First off, we're going to start off with our free body diagram again, because that's what we need in order to do any forces problem. It's going to help us out tremendously. Again, the first force that I'm going to start off with here is going to be the force of Earth on the object. Last time I checked, if I drop something, it's going to fall straight downwards. So I'm going to have here Fg straight down. And again, we know this is the force of object on object. The object that creates this force is the Earth. So this is going to be the force of Earth on the block. Then I'm going to have all contact forces once more. So the main thing I'm in contact with here is going to be the ground. That is going to exert a force upwards on the block, and that is going to be normal force Fn. And again, Fn is going to be the force of the ice on the block. Then we are going to have here, I am pulling the block with a rope to the left. So that is going to be a force of tension, or the force of the rope. That is going to be a force to the left there, Ft. That is going to be the force of rope on the block. Then my last force here, since I've been told it's not a frictionless surface, hasn't said anything about frictionless, even though we're on a sheet of ice. We have actually a coefficient of friction for that on the reference table. So that means we're going to have friction to the right here, because it is in the opposite direction of motion. Since we are moving to the left, my FF is going to be pointed to the right, and that is again going to be the force of the surface on the object, which is going to be the force of ice on the block as well. So let's move into part B of this example. All right, so part B, fairly similar to part B from number 1, is the block in a state of equilibrium. So you can definitely go ahead and try this yourself as well. We know again, we're going to start off with our evidence or our fact of physics. We know that equilibrium is when an object is moving in a straight line at constant speed. This includes an object at rest. So we have our evidence here, or our fact of physics. Now we're going to make our explanation based on this, or since this is happening, we are going to be making our claim based on that as well. So since what is happening here? We have the rope is pulling us at a constant velocity across the sheet of ice. So that means we are, the block is being pulled in a straight line at constant speed. That's our reasoning. We can then make our claim based on these two things, that our block is going to be in a state of equilibrium. And again, we are not moving up or down, so that means our vertical forces are also going to be equal to each other, as well as the horizontal forces. Alright, so moving into part C of my example, I'm going to calculate the magnitude of the force needed to pull the block at a constant speed to the left. And again, we're going to show our work including the equation and substitution with units. So you can see here on the left side that I have my free body diagram from earlier. I also have the approximate coefficients of friction from the front page of the Regents reference table. I'm going to link this down in the description down below. We're going to use this because we haven't been given the coefficient of friction in the example, but we've been given a rubber block that is on ice, and that is one of the two surfaces or two interactions that are on this table. So again, since we are in equilibrium, we know this from part B, we are going to start off here with my left forces equal right forces equation. And my free body diagram is going to tell me which forces these are. So my left force is going to be Ft. My right force is going to be Ff. And with this, Ft is going to be that force that I'm going to need to pull to the left with in order to get this at constant speed. So that's what I'm looking for here. Again, we know that the equation for Ff, based on the reference table or from our facts, is the coefficient of friction mu times the normal force Fn. So I'm going to plug that in there for Ff. So Ft, the force that I'm going to pull with, is going to be equal to mu Fn. Again, we don't know what Fn is, but we can use our free body diagram to look at that. So we're going to see here again, we're not moving up or down. So I can have there my up forces equal my down forces. My up force is going to be the normal force Fn. My down force is going to be the force of Earth on the object, Fg. So then I can plug that into my equation here. So we have now that Ft is equal to my frictional force, mu times Fn, which we know now is Fg. Then, since we are given the mass here, I can't just plug in 5 kilograms for Fg because that is not newtons. I need to convert this to newtons. So I need to have my equation here for Fg, which is mass times the gravitational field strength. So I'm going to have here Ft is equal to mu times the equation of Fg, which is mg. Again, it's also on the Regents reference table, just written out a tiny little bit differently. Then I can now plug in with my units. So again, the first thing that we need here is my coefficient of friction. So on the reference table, the approximate coefficients of friction, we have here rubber block on ice. We can look here on the approximate coefficients of friction, look for rubber on ice. We have here kinetic is going to be 0.15. So that's what I'm going to plug in for mu here. Then my mass is 5 kilograms. That's easy. That's given to us in the question. And then G, you can either use 9.81 if you like. That's on the front page of the reference table. But I'd rather use 10 newtons per kilogram. That's also totally valid because it's just much easier to work with. And it's able to be used on a part 2 for the Regents as well, or even on a part 1. So we can plug that in here. We have our coefficient of kinetic friction, 0.15, times my mass of 5 kilograms, times my gravitational field strength, 10 newtons per kilogram. You're going to plug this into your calculator to 0.15 times 5, then times it by 10, and end up with your answer here of frictional force, or the force that I'm going to pull with, which is equal to my frictional force, is going to be 7.5 newtons. So I hope these examples were helpful, and see you guys in class.